All right, looking at the non-calculator questions, hopefully these will be a little bit quicker than that last calculator question. Let's see. We have a function f that is given. They do tell you that f consists of 3 line segments, which you probably would have guessed, but they always put that in there just to make sure you understand that there's no very small curvature to it. This thing right here I consider extremely beautiful. That is an integral defined function, and integral defined functions are the easiest thing in the world to find the derivative of. So I'm going to go ahead and make a note that g prime of x is derivative of negative x is negative 1 plus, and then the derivative of that antiderivative, plug the x in for the t, and technically you multiply by the derivative of what you plug in. The plus 1 really isn't necessary, but I'm just killing it dead there. I have a sneaky suspicion that A is a typo because it says find g of x and g prime of x, which doesn't make sense because g of x was given. So hold on a second. Let me look this up and see if those should be actual number values instead of a variable. Okay, when I looked at the source of this question, yes, those are supposed to be numbers, so I'm going to erase those. That's supposed to be a 3 for each of them. It's g of 3 and g prime of 3. So let me make that change. And then for g of 3, that is simply going to be, you just plug in 3 for the x's. So g of 3 is going to be negative 3 plus the antiderivative from 2 to 3 of f of x, of f of t, dt. And that'd be negative 3 plus the antiderivative from 2 to 3 is simply the area under the curve from 2 to 3, and that is 1/2. Negative 3 plus 1/2 is negative 5/2. So there's g of 3. G prime of 3 is going to be a little bit easier, especially since I have gone ahead and found the derivative of g. G prime of 3 is going to be negative 1 plus f of 3. Negative 1 plus f of 3 is simply the y coordinate at 3. This is the graph of f of x. Always identify your graph. And f of 3 is 1. Negative 1 plus 1 is 0. Let's see. Number B, find the x coordinates of the 3 critical points of G and show the computation that leads to your answers. So number B. We'll see, I'm going to erase that because that was my work for A. If I want critical numbers, you always set the derivative equal to 0. Always, always, always write your equations. So negative 1 plus f of x needs to equal 0. That's going to be whenever f of x is equal to 1. And I can look at this graph and I can tell that f of x equals 1 3 times, which they said there were 3 of them. At 1, 3, and that would be 4.5. So x equals 1, 3, and 4.5. Number C, find g double prime in terms of f. That's going to be pretty easy because I already have g prime of x. Found that earlier. G double prime is going to be the derivative of negative 1 is 0, and the derivative of f of x is f prime of x. So g double prime is f prime, and that is all you have to do for part C. That was nice. That would probably only be worth 1 point. And then finally, number D, for each point you found in part B, so that'll be 1, 3, and 4.5, determine whether we have local max, min, or neither. And we have a couple of options here. We have the first or the second derivative test. First derivative test is when you look at the sign chart and you determine where the function increases or decreases. Second derivative test is actually going to be easier in this case because I have such a nice clean second derivative. So my second derivative test is where you use concavity to determine if critical numbers are local extrema. So I will test for x equals 1. I need to find g double prime of 1, which is the same thing as f prime of 1. And f prime of 1 means the slope of f at 1, and the slope of f at 1 is negative 1. If my second derivative, g double prime, is negative 1, that's a negative number, that means g is concave down, and a concave down function at a critical number means you're looking at a local max. So therefore, local max at x equals 1. So there's one of the conclusions. That is with the second derivative test. x equals 3. The second derivative of g at 3 is the same thing as f prime of 3. And the slope of f at 3 is 1. That is a positive number. That means your function g would be concave up. And if your function is concave up at a critical number, you have a local min at that x coordinate. All right. And then finally, we plug in 4.5 and g double prime of 4.5 would be the same thing as f prime of 4.5. And the slope of f at 4.5 is negative 2. That is a negative number. And if your second derivative is negative, that means your function is concave down, and we have a local max at x equals 4.5. It does say justify your answer. This is one of those problems where since I headed my work with second derivative test, I have shown where I've plugged my points into the second derivative. I've identified whether it's positive or negative, and then my conclusion. Your work is probably sufficient, but if you wanted to kill it dead, you could say, after each one of these, you could say, by the second derivative test, which I've already kind of set up there, but whatever. So all of this is by the second derivative test. The second derivative test does not find concavity. The second derivative test finds local extrema, and it uses concavity to find the local extrema. Okay, good? All right. Number next. A train initially stops, begins moving. The table below gives the train's acceleration. Always pay attention to what you're looking at. It's the acceleration. They do label it there, miles per hour squared. We're only going from 0 to 1, and that is f of x. Hey, I love functions like this. If that's, ooh, this is interesting. Okay. If that's f of x, then f prime of x, I can just plug in. F prime of x is a of x. Okay? So I'm going to make that note. It's very easy to find derivatives of integral defined functions, so I'll go ahead and find that. I might use that later, I'm not sure. Okay, use the midpoint Riemann sum with 5 subdivisions to approximate f of 1. So a, f of 1 would be, well, we just plug in 1 for the x. That'll be the area from 0 to 1 under a. Now we don't have an actual equation for a, so we cannot get an exact answer. That's why they said use Riemann sums. And Riemann sums with 5 subintervals. Your delta x is going to be b minus a, divided by the number of subdivisions, which is going to be 1/5 or 0.2. So each of my rectangles is going to go like this. So it's going to be 0.2. That's the base of each rectangle. If the base is the same throughout, then you could factor out that base. Now I simply need to add the heights, and we're using midpoints. So I'm going to use the value at the middle of each of these intervals. And so that would be 0.2 times 90 plus 80 plus 80 plus 40 and 10. And then we could clean that up. I'm going to pause the video while I do that. All right. Now that is 60. You always need to include units if units are provided. We found the antiderivative of acceleration, which would be velocity, and velocity in this problem would be measured in miles per hour. So it cleaned up to 60 miles per hour. Again, y'all know this, but on the AP exam and on my test, you do not have to simplify. So I actually could have stopped with 0.2 times 90, 80, 80, 40, and 10, but I decided to go ahead and clean it up just because I could. So there's A. Number B, explain what f of 1 is and give its units. That's kind of what we just did. I've already given the units, so maybe we didn't need units in part A, which would be kind of silly to me, but f of 1. Now when it says explain what it is, that doesn't mean repeat the answer. They don't mean say that f of 1 is 60. By the way, we don't know that f of 1 is 60. That was an approximation. F of 1 would be it's the antiderivative of acceleration. Therefore, f of 1 is the velocity of the train at time t equals 1. And it's measured in miles per hour. So that would all be all you have to do for part B. And then finally C. I'm trying to keep the different sections color-coded. Okay, assume that f of t. Now remember, f of t we've just established as velocity, so we could make a little note to ourselves that f of t is the velocity of this function, of this train. So when it says f of t is constant, that means velocity is constant on the interval 1 to 3. Okay, so now we're going beyond the time interval 0 to 1. So we're going from 1 to 3. And the f of 1 actually is equal to the Riemann approximation that we got in part A. So we are now going to say that f of 1 is actually equal to 60. How far does the train travel on the interval 1 to 3? And then show how you arrived at your answer. Okay, if you want to know how far something travels, this one's going to be extremely easy. The distance something travels would be the antiderivative of velocity, right? So distance is the antiderivative of velocity. Now, technically, total distance is the antiderivative of the absolute value of velocity. You want to make sure you're measuring total distance and not displacement from point A to point B. Now, in this problem, they told us that f of t is constant from 1 to 3. Well, if it's constant and we know that f of 1 is 60, therefore, so I can take this and I can say with confidence that my velocity function f of t, which is the velocity, is going to equal 60 for the entire interval 1 to 3. So if I'm going to find the distance traveled from 1 to 3, that's going to be the antiderivative from 1 to 3 of my velocity function, which is just 60 dt, which would be 60t from 1 to 3, which is going to be 6 times 3, which is 180, minus 6 times 1, which is 60, or 60, which is 120, and that would be measured in miles because we are measuring distance. And I kind of went the long way around the world to get that one because this is a calculus test. It's a calculus class, so I used calculus to answer it. However, we could have gone old school algebra 1. Since velocity is constant and we're traveling for 2 hours, we could have simply done or total distance is rate times time, where my rate was 60 miles per hour, and that was constant, times the amount of time we traveled, which would have been 2 hours. And the hours would cancel, leaving you with simply 120 miles. And that would have been an acceptable way to do it also, but it's very rare that you get to use Algebra 1 to answer a calculus question. So I chose to show you the original way because this method works every single time, even if the velocity is not constant. So that's why I chose to go the long way on C there. Let's see, 35, we have 2 more. See, water is pumped into an underground tank at a rate of 8 gallons per minute. Now that is a rate, 8 gallons per minute, and leaks out at another rate of root t plus 1 gallons per minute. Okay, when I see a question like this, these questions have become increasingly popular in recent years on the AP exam, where you are given a rate in and a rate out. In this case, the rate in, water is pumped into the tank at 8 gallons per minute, and it is leaking out at the rate of root t plus 1. If you know the rate that something's going in and the rate that it's going out, then the total change is going to be the rate in minus the rate out. So it's always going to be in minus out, and in this case that would be 8 minus the square root of t plus 1. Now that is the total rate of change that it factors in the rate in and the rate out. So I'm just going to make that little note to myself right now. It probably will come into play later on. Let's see. We're only going from 0 to 120. At time 0, the tank contains 30 gallons of water. So they give you an initial condition. So they give you the initial condition of at time 0, we have 30 gallons of water. And if you read through the problem, question A asks how many gallons leak out from 0 to 3. B is how many gallons are actually in the tank at 3. Part C, they actually define a new function, A of t, which is the total amount of gallons. So this initial condition, since they have defined the function A, they're saying here that my amount at time 0 is 30. And if A is the total number of gallons of water in the tank, then this total change function is the rate of change of the total amount. So that 8 minus root t plus 1 is actually the derivative of A. That's the total change. And so I've done a lot of work ahead of time that probably is going to save me some thinking later on. All right, so now let's go on and answer the question. How many gallons leak out of the tank from 0 to 3? Well, we know an actual amount, and we're only looking at how much has gone out of the tank. So I don't really care about how much the rate that it's going in, but I do know the rate that it's going out. So to answer this one, it would be the antiderivative of the rate out, and we're going from 0 to 3. This is a fairly straightforward antiderivative, so I'm going to pause the video and work this one out. All right, there's your answer down here. If the inside derivative is 1, don't forget that if the inside derivative is 1, you don't have to go through with u sub. You could just treat it like a giant x. The antiderivative of x to the 1/2 is x to the 3/2 divided by 3/2. You just have to keep the inside the same. You do end up with a final answer of 14/3, and the units would be gallons. Even though the question kind of implied the units, I still like to write it. And you didn't have to simplify it, but I've done this problem before, and I know that I'm going to need that answer later on. So there is your simplified answer. Number B, how many gallons of water are actually present in the tank at time 3? And here is where I am going to take advantage of some work that I have already done. I know the derivative A prime. I also know my initial amount at 0 is 30. So if I want the amount of water in the tank at time 3, then I could say that A of 3 would be my initial condition, A of 0, plus, and then the area under the total change, A prime, from 0 to 3. And then I can work that one out. This is going to be very nice because part of that A prime I've already done. So that's going to be A of 0 is 30, plus the antiderivative from 0 to 3. A prime is 8 minus the root of t plus 1. And since I have already calculated the area from 0 to 3 of root t plus 1, I'm going to split this up. 30 plus area 0 to 3 of 8 dt minus area 0 to 3 of root t plus 1 dt. This answer right here I already know is 14/3. 30 is a constant, so I simply need to do this antiderivative to finish it. That's not going to be too bad. That's 8t from 0 to 3. 8 times 3 is 24, minus 8 times 0, and then we'll add all those together. So 30 plus that minus that, that'll be what, 54 minus 14/3. I don't feel like simplifying that. I don't think I'm going to need this answer later. So A of 3 is that many gallons. There's your answer to part B. And there are other ways that you could have solved that, but I'm choosing to work it in a way that will work for any of these types of problems where you have a rate in, rate out. The fact that these functions are nice, would you stop dinging at me, stupid phone? The fact that these functions are nice opens up some other doors where you could have gotten this answer, but this method would work even if you have an incredibly ugly antiderivative problem and you're allowed to use a calculator or something like that. So those of you who are watching this and you know how to do this and you're wondering why I chose that route, that's a brief and kind of a half explanation as to why. All right, number C. Number C, I need to write an expression for A of t, the total number of gallons of water at time t. Well, we kind of just did that. Notice in B, we answered that question. We want to know the total number of gallons at time 3. Well, now it's the same question, only it's at a general time t. So it's actually going to be the same thing as part B, but A of t is going to be my initial amount plus the area from 0 to t. Instead of 0 to 3, I'm now measuring the amount at any time value of a prime of t. But again, kind of like a problem that I worked earlier, you are not allowed to have the same variable for the limit of integration as you are the integrand. So I'm simply going to take the t's here and turn them into something else, like maybe an x. And I would clean that up into 30 plus area from 0 to t. And my a prime, I guess I'll go ahead and throw in the actual equation. Root t plus 1. Can't use t's. Has to be an x. dx. And that would be an expression that would give the actual amount of water in the tank. Again, this could have been done a different way because the antiderivative of my a prime is very easy. You could have actually come up with some kind of a polynomial or some actual function that doesn't involve an antiderivative, but I'm choosing to do it this way because there are some problems on the AP exam and on my test where the expression to find the total amount has to include an integral. So this method works all the time. There are other methods that work sometimes, and I'm choosing not to work those problems. All right, let's finish this one up with part D. And let's see, I just took like a 10-minute break there when I paused it, so if I seem disjointed there. All right, at what time t is the amount of water a maximum? We are on a closed interval, and it asks for a maximum. We're going to use the extreme value theorem for part D. Now, all maxima will occur at critical numbers or at the endpoints. So I'm going to first find the critical numbers, which means I need to set my derivative, a prime, which is 8 minus the square root of t plus 1, equal to 0. That means 8 needs to equal the square root of t plus 1. 8 is the square root of 64, so if I can make t equal to 63, I have my critical number. Then once you find the critical number, you need to test the amount of water at the critical number, and you need to find the amount of water at the two endpoints, which are 0 and 120. And we can do that by plugging into my function right here for a of t. A of 63 is going to be 30 plus the area from 0 to 63 of 8 minus the square root of x plus 1 dx. A of 0 was actually given, that's 30, so we don't have to worry about that one. And a of 120, same thing, plus 0 to 120 of 8 minus the square root of x plus 1. And we are looking for the time where we have the most water in the tank. And we'll have to work out a of 63 and a of 120. And the bell just trying to start a class. I'm going to have to pause it before I get back to this, and it'll probably be a long break again. But you won't know because I'm just going to pause it and unpause it real quick. Okay, and pause the video like 3 hours ago. But I started working this problem out, and my setup was fine. There was nothing wrong with what I did. As I started working this out, you can see right here, down here I started working a of 63. I found the antiderivative right here, so I could use the antiderivative for both a of 63 and 120. However, the arithmetic on this gets absolutely brutal, and this is a non-calculator question. I went back and checked the source, and I was right. It is a non-calculator. So while this method would work, the extreme value theorem will work, because of the ugliness of it, I'm going to abandon this process where you actually work out the antiderivative. I'm going to abandon that, and I'm going to go back to another approach. I'm going to get rid of this. While it was all good math, nothing wrong with it, it just gets brutal. So what I'm going to do is I'm going to use that critical number, and then I'm going to think, all right, well, if that's my derivative and that's my critical number, I'm going to go into the old-fashioned first derivative test, where I will plug in a point to the left. So a prime of 0 would be 8 minus the square root of 1, which is positive. And if I plugged in something after 63, now remember, you want something that's going to be a nice perfect square. So I know the square root of 81, so I'm going to say, let's plug in 80. A prime of 81 would be 8 minus the square root of 9, which is negative. based on that, I know that there is a local max at 63, and because my function is increasing on the left to 63 and decreasing forever after, I also know that at 63, my amount will be larger than the two endpoints, 0 and 120. So that's pretty much the question. It just says at what time t is the amount of water at a maximum. I abandoned the extreme value theorem, so I'm going to get rid of that. So I'm simply going to say my derivative, a prime, is greater than 0 on the interval 0 to 63, and a prime of t is less than 0 on the interval 63 to 120, and because of that, I know that there is a maximum at t equals 63. Again, nothing wrong with that original setup. It just ended up being butt ugly, so we're not going to worry about it. The last problem I'm not going to have time to record. However, if you go to my web page, I worked number 36 for both of the BC classes. If you go to my web page for the notes on December the 9th, this Tuesday, if you scroll down, if it loads, there it is. Scroll down to either 5th or 6th period, and you will see right there is the worked out solution for number 36. I suppose I could just take a screenshot of that and keep it on my notes, put it on that PDF. So I'll do that. Screenshot, oh, where's my screenshot tool? There it is. And I'll just copy this so that the PDF that I'll link on my webpage will have the correct answer. Alright, so there you go. That is all of the answers to the review. Hopefully the video will help out some. There, I think I'm good. You know what? Alright, that's good. I'm going to quit recording.